Okay.
So the next speaker is Julia Koch. She will present a paper on the Bootstrap inference for group factor models. Julia, the floor is yours.
Okay. Thank you for introducing me. My name is Julia, and I'm a PhD student in McGill University. I'm glad that I can present our paper that goes by Bootstrap inference for group factor model. This is joint work with two professors, Sylvia and Benoit. So first of all, I would like to talk about what motivated our work. We are working on group factor models, which is an extension of the factor models. Factor models are very popular in economics and finance field for the tool to reduce dimension in a big data set or to forecast with many predictors. And the group factor models, which is an extension of the factor model, allow for different groups to share group common factor as well as group specific factors. So for example, if we have mixed frequency setting where we have one data set containing high frequency variables and the other data set containing low frequency variables, and group factor model can help us to capture the co-movement between this two frequency data set as well as high frequency specific factor and low frequency specific factor. Also, we can use the group factor model for data set of individual stocks and a data set of portfolios so that the group common factor can represent the stochastic discount factor. And in our paper, we propose a Bootstrap test for the number of group common factors. In fact, our test is a Bootstrap version of the test that is proposed in Econometrica paper by Andrea Gagliardini, Geisels, and Ruby in 2019. Henceforth, I'm going to refer their paper to AGGR and their test to AGGR test. But why do we propose the Bootstrap method? We have two main reasons. The first reason is that the AGGR test is an asymptotic theory-based test, which means they use critical value from the standard normal distribution. And normally the normal distribution does not behave that well in a finite sample, and Bootstrap can improve this part. The second reason is that the test statistic they propose is quite complicated because there is an asymptotic bias involved because of the estimation of the factor in the first step. Also, there is an asymptotic variance, which is quite complicated. So if we want to obtain like the feasible test statistic where we have to replace the bias and the variance with its estimators, it's going to be quite complicated to obtain these estimators. So our paper is focusing on to propose a simple Bootstrap method so that we do not have to estimate the bias nor the variance. So moving on, I would like to introduce some notations for the group factor model. We focus on two groups where each group contains N1 different series for the first group and N2 different series for the second group. Then each group can be represented in a factor structure as you see in equation 1. The highlighted part F1T and F2T are the factors in each group. And the group factor model can help us to that factors share group common factor, as you see in the highlighted part. So the factors in each group contain two different factors again, where the first one is the group common factor that is common between groups and the group specific factor. Then using this decomposition for the factor, we denote the number of common factor in each group by Kj, J for the group, which is the sum of the number of group common factor Kc and the number of group specific factors. Then again, our goal is to test the number of common factor, which is the dimension of this FTC. And this FTC can take, the dimension of this FTC can take minimum 0 to maximum K underline, where the K underline is the minimum of the number of two factors. So to identify the number of group common factor, the AGGR proposed simple method which is based on canonical correlation. The canonical correlation is like a generalized version of the correlation coefficient. If we have just one factor for each period, so those factor F1T and F2T are scalars, then the canonical correlation is same as correlation coefficient. If it is generalized, such as 2×1 and 2×1 for each factor, then the canonical correlation is same as eigenvalues from the covariance matrix of these two factors. Then AGGR shows that if we truly have KC common factor, then this KC largest canonical correlation we can obtain should be equal to 1, and the remaining should be strictly less than 1. Then using this insight, we can construct the null hypothesis of testing KC common factor by denoting the order canonical correlation by rho in a decreasing order, because the largest canonical correlation should be equal to 1. So to test KC common factors between groups, we construct the null hypothesis as KC largest canonical correlations are 1. And based on this null hypothesis, we construct our test statistic as the difference between the sum of canonical correlation and the number of common factor we test, which is KC. Then under the null hypothesis, the difference should be equal to 0. However, in the sample, because we do not observe the factors will be replaced by its estimators. So for example, F1T and F2T will be replaced with its F1T hat and F2T hat. And the canonical correlation will be based on these estimators. And the test statistic will be the sample analog of this equation 2. Then we can use the normal distribution to decide to reject the null hypothesis or not, because AGGR shows that the test statistic follows the normal distribution as you see in equation 3. So if we see equation 3, in the parentheses, these two terms are the test statistic. So the remaining part derives the mean of the normal distribution, the highlighted part. So we can see that there is an asymptotic bias involved. The another part that is highlighted is the asymptotic variance we denote by omega. And the another thing to notice is that the convergence rate is n square root t, which is quite non-standard in the factor literature. However, this bias and the variance are unknown. Therefore, if we want to obtain the feasible test statistic, we have to replace them with its consistent estimators, where we denote as b hat and omega hat. Then using these estimators, we can construct the feasible test statistic by rescaling the third equation with the variance estimator. So we denote the test statistic, feasible test statistic by psi tilde. And because it follows the standard normal distribution, we can obtain the critical value from a standard normal distribution to decide to reject the null hypothesis or not. The problem is that this bias and the variance have complicated forms because it depends on the idiosyncratic error term. More precisely, it depends on the cross-sectional dependence and the serial dependence. Even in AGGR, in fact, they assume a quite restrictive setting to propose their estimators, where there is no serial and cross-sectional dependence. So in our paper, we propose Bootstrap method so that we do not have to estimate these estimators at all. And we propose a simple wired bootstrap, residual-based wired bootstrap, where we can write our Bootstrap data generating process as you see in equation 5. So using this residual-based bootstrap, we replace the factor loadings and factors by its estimators. And for the idiosyncratic error term, we use the resample version of the residuals in the factor model. Then the resampling method that we use is the wire bootstrap, where each component of this epsilon JT star, because it's a vector, is the multiplication of the residue and a random variable from an IID standard normal distribution in the bootstrap world. Another thing that we use is that we impose the null hypothesis to construct the bootstrap data generating process. More precisely, we follow some steps for the testing in the bootstrap world. In the first step, we estimate the factors using the bootstrap constructed data set Y star using principal component analysis. Then we can denote the estimated factors as F head star. And using these estimated factors, we can obtain KC largest canonical correlation that are denoted by rho head star. Then in the third step, we construct the test statistic in the bootstrap world. By repeating these three steps for capital M times, we can obtain the bootstrap p-value by comparing the test statistic in the original sample and the test statistic in the bootstrap sample. And using this bootstrap p-value, we can decide to reject the null hypothesis. As you see in this testing procedure, we haven't talked about how we estimate the bias and nor the variance, which means we do not have to go through that step using the bootstrap. However, of course, the bootstrap is not a magic tool. We provide a set of high-level conditions so that the bootstrap produces a valid bootstrap p-value. In effect, the high-level conditions we provide is that the asymptotic bias in the bootstrap world should mimic the bias term in the original asymptotic distribution. Also, the asymptotic variance in the bootstrap world should mimic the original variance. For the wire bootstrap that we propose to satisfy this high-level condition, we provide a set of primitive condition as well. In fact, this primitive condition is that the idiosyncratic error terms are not serially nor cross-sectionally dependent. It's because the way we generate the wire bootstrap, because the wire bootstrap generates the idiosyncratic error term in the bootstrap using the random variable from the IID standard normal distribution. However, in the paper, we propose an extension of the wire bootstrap, which can allow cross-sectional and serial-dependent bootstrap idiosyncratic error term. Finally, I would like to show you how the bootstrap method performs in the finished sample compared to the AGGR test. So we consider two different data generating process where the first DGP is we have one common factor, but no group specific factor. So under DGP1, we want to have this F1TS and F2TS, as well as this factor loadings for the group specific factors. And DGP2, we now consider one group specific factor as well as one common factor. All the variables are simply IID standard normal distribution. We vary the sample size from 50 to 200. We use a replication number for 5,000 and bootstrap replication number for 399. We report the results for 0.05. And this is our simulation result for DGP1 and DGP2. Since the report are based on 5% rejection area, if we have the results close to 5%, it means it's good. The first panel shows the DGP1. The row A stands for AGGR test, the row WB stands for the wire bootstrap. So for the DGP1, where we have no group specific factor, AGGR test and wire bootstrap both performs pretty well. They are close to 5 for all samples. DGP2, as we add one group specific factor, the AGGR behaves poorly as it shows a large size distortion. However, while Bootstrap still works pretty well. So I would like to conclude our presentation. In our paper, we proposed the Bootstrap method as an alternative inference method for the testing the number of group common factors in the group factor model. We provide a set of high-level conditions under which a simple Bootstrap method is valid. And using the Bootstrap method, we don't have to estimate the bias and the variance we see in the asymptotic distribution. We verify this condition in the case of the while Bootstrap, and we show that the Bootstrap performs pretty well compared to AGGR tests in the finite sample using the Monte Carlo simulation. Thank you.
Thank you, Julia. Does anyone have a question? Or... I have a quick question. Your synthetic variable epsilon is drawn independently for the two groups?
Yes, for now we consider independence between two groups.
Okay.